Last class we have discussed about canonical transformations, and today we are going to apply canonical transformation in harmonic oscillator problem. So first we know that what is a Hamiltonian for a harmonic oscillator? It will be Hamiltonian is T plus V, and your T will be half mv square, and you are going to replace this v in terms of p, and so your Hamiltonian for a harmonic oscillator is h is equal to half k q square plus p square by 2m, and this harmonic oscillator is fixed at one end and you are having a mass attached through a spring with the spring constant small k. We are using the notation small k here. So you know that omega square is equal to the frequency square is equal to in terms of root of k by m. Omega is equal to root of k by m, or omega square is equal to k by m. So using these values in the Hamiltonian, you are getting it as 1 by 2m m square omega square q square plus p square. And you know that this is a sum of squares. You can see this part. This is a square and this part is also a square, and the sum of these squares will suggest that this h is cyclic. Hamiltonian h is cyclic in new coordinates. Okay. Now you are going to try a canonical transformation of this form. So here we are using a trial approach, and you are going to find or try a canonical transformation which can be used to solve this harmonic oscillator problem. For that you are having one you can see that P is represented in terms of new coordinates capital P and capital P, and Fp defines a function that can produce canonical transformation, and Q is another function and Fp, and you know that m is the frequency of the oscillator, and again P in terms of Fp and Q. So Q is represented in this manner, and here you can see that this is the amplitude and this part is the amplitude of Q. Now I can define this. So we have seen that h is cyclic, which means that it is a conserved quantity or a constant quantity. So I can say that this h should be equal to the new Hamiltonian since it is independent of time. So I can represent this new Hamiltonian, and that new Hamiltonian is you have to substitute the sum of the squares. So you are getting it as f square p by 2m, and you can see that in this part, is there any old coordinate or q is there any q, capital Q? No. So you can say this Hamiltonian, new Hamiltonian, is cyclic in q which is the new coordinate, and this happens because of the conservative nature of Hamiltonian h, the old coordinate. Now we have to find Fp. So this is the function which generates canonical transformation, and so you have to find Fp, and for that you have to consider the generating function. Here you can see that you have to find Fp, and k is cyclic in q. So your function or generating function should have capital Q, and other part can have Q. So F1 in this manner, this is a trial approach. you can use this method to find the generating so F1 is the generating function which can be used in such a manner to make the above canonical transformations. So you know what is P from type 1 case. This is already we have seen in the last class. For type 1 you get P as equal to dou F1 by dou Q, and this is equal to, here F1 is this quantity and you have to find dou F1 by dou Q. So this is equal to m omega q cot Q, and next capital P minus dou F1 by dou capital Q, and which is equal to minus half m omega q cosec square m omega q square by 2 sin square q. And so you are getting it as in terms of small p and capital P. And what is the generating function F1? How generating function depends on, or which are the variables? Small q, capital Q and T, and you are having this P instead of and capital P. Okay. And you can rearrange this equation to get small q. You are going to rearrange this equation and you are getting small q equal to root of 2p by m omega sin q. And now you are going to substitute this q, this q in equation 7, which is your p. So now your p is equal to a quantity in terms of new p and new momentum coordinate and position coordinate. So here small p, which is the old coordinate, which is converted in terms of new coordinates p and capital P. So you can now compare this equation 10 with equation 3, which equation 3 is also p is equal to a function of f into p cos q, capital Q. And if you compare this term with the newly generated p, then you will get it as, there is a cos factor here. So the other part represents the function of p, and that is equal to root of 2p m omega. So you are getting this function fp in terms of capital P. Now you can find the new Hamiltonian. New Hamiltonian is f square p by 2m, which is equal to, if you substitute the values of f square capital P into omega. And what about k is actually your new Hamiltonian, but it is equal to h, or you can say that the new Hamiltonian is equal to the total energy of the system itself. Since this is a conservative system, again it is a conservative system, and Hamiltonian, Hamiltonian is cyclic in nature. New Hamiltonian is also cyclic in Q and capital Q, and so you can say that h, this is the old coordinate, is equal to k, the new coordinate, and is giving you the total energy of the system, and that energy should be a constant or conserved. That energy should be conserved. Therefore, we can say that the equation of motion, what will be the equations of motion? Q dot is equal to dou h by dou k by dou capital P. This is your one equation of motion, and that equation of motion becomes becomes omega, because we know that k is equal to p omega. So from that you are getting it as omega itself. So q dot, which is equal to dou k by dou p, is equal to omega. So this quantity gives you the frequency of oscillation. So new coordinate, derivative of new coordinate will give you the frequency of harmonic oscillator omega. And this, you can get this, the solution for this equation can be represented in terms of, how can I represent this solution for this equation? This will be, the solution will be q. So that q should be, from integrating this q dot, you will get the solution for this equation as omega t plus alpha, which is a constant of integration, and you can apply the boundary conditions to find alpha. You can apply boundary conditions. So now you can substitute. So you are going to find q and p using this equation. Equation 13 is your p, capital P, and which equation should be 15, which is capital Q. So you can use this equation and capital P. So using capital P, the new coordinates, new momentum coordinate, and Q, capital Q, which is the new position coordinate, and using these two equations you are having an equation for old coordinate. So this old coordinate is equal to root of 2e by m omega square, and here it is sin q. Instead of q you are replacing it with omega t plus alpha. Anyway, this is an angular quantity which is varying from 0 to 2 pi. And p is equal to root of. So you can see that these two equations have, one have a sine function, one is a sine function and the other one is a cosine function. So can you plot a graph with q as y axis and t along x axis? Can you? So first you have to draw a graph with q along small q, the old coordinate. So this is q. This mentioned, okay. So yes, good. And this is the plot for q versus t. Thank you, thank you, Anaina. Please come. Now you have to plot small p versus t. You can rub that dot, please. Versus, this is the variation of old coordinates with respect to t. Okay, so good. Anyway, Meenu and Anaina, thank you. And now can you plot new coordinate q? What will be the new coordinate? You can see this is your new coordinate. You have to plot capital Q versus time. So this is your equation. Okay. So can you explain it? Please explain it to. It's correct and you can explain it.
Q is equal to omega t plus alpha. So it will be increasing and it will not be constant because there is a factor alpha.
So even if time is equal to 0, alpha is there. But in certain cases, you can have this constant of integration as equal to alpha when the boundary condition is like that. But here you cannot say that it is 0 or you cannot say at time t equal to 0 it is 0. So you have to represent in this manner. Okay, it's right. Okay, thank you.